Welcome back to System Software. All right, so how was your week? How was setting up virtualization in Vagrant? Was that fun? Raise your hand if it was fun. Raise your hand if it was painful. All right, so just installing software, you'll notice, is not so straightforward. This is where having experience and knowing your tools, knowing your system, knowing how installation works is really useful. We kind of take it for granted. But I think it's a good experience to actually figure out how to do this. It seems a lot simpler than it actually might be. So let me take a quick survey. How many people have Vagrant and VirtualBox successfully set up? So it looks like a majority, but definitely not everyone. Who would like to admit it, is still struggling to get it set up? Okay, so it's pretty few. So it's okay if you haven't finished it for the assignment today. The assignment today was really just to get you to get this set up so that when you're actually doing the assignment, you're not struggling with stuff that's not the assignment. And so that brings me to the next topic, which is office hours. If you've ever tried to schedule a meeting with like 5 people, you know how impossible it is. Try doing that with like 253 people, 254 people. It's very hard. So what I think I've landed on, and I want to take a quick survey to see if this is suitable, is I've moved my office hours to Mondays and Tuesdays at 1. And then the TA will be Wednesdays, 12 to 2. So do my hours work for you? Raise your hand if they work. Okay, it's a majority. Who definitely does not work for? So small number of people. So I'm very sorry. Use Ed Discussions and just email me or send me email me or ask me on EdSTEM to set up an appointment if necessary. Or, so for those of you who can't come to my office hours, can you go to the TA's office hours? Who cannot go to any of these office hours? Okay, so there's only a couple. So email me if you need to meet. Or we can meet after this class if there's time. So very sorry about that. It was very hard to get even these hours to figure out. Maybe I should do like a poll of everyone, and everyone puts their hours. Of course, there's going to be no one spot probably, except maybe like 1 a.m. Okay, but yeah, message me if you still have any issues with office hours or coming. Message me. I want to make sure that every student is able to get some appointment. So we'll, okay, so I think that's pretty much settled with a few. Almost everyone, but not everyone, unfortunately. All right, so that's office hours. That'll be the new office hours. I'll post the rooms here. So my room is I'll post everything here once now that this is settled. I just posted homework 2. Sorry for not doing that before class, but I posted homework 2. It'll make more sense after today's class. This is the kind of thing where if you know the command line tools, this is very easy. If you don't know them, it's impossible. So today I'm going to go over a whole suite of command line tools. For some of you, this may be review. For some of you, this may be mind-blowing that you can even do this on a machine. And most people will be somewhere in between. But this is the homework for next week. Hopefully it's pretty straightforward, but we'll actually have office hours next week where hopefully most people can come. So if you have any issues, feel free to come to office hours. We'll also have lab today where the TA can go over any questions you have about this. All right, so a large chunk of people have gotten Vagrant and virtualization set up. Who is on Ed Discussions? Okay, good, a nice healthy majority. Who's definitely not on it? A small number of people. So join it. This is much faster to ask questions and get a response from me. My email inbox is brutal this semester. This I check. I can poll it, and I can check for questions. And we have also the graders and TA on there as well. If you're having trouble with Vagrant, then chances are somebody else had that problem. There's lots and lots of little sort of twiddly things you have to do in order, especially in Windows. So I don't have a Windows box. I should probably try to do this in Windows as well. But your antivirus might be blocking the connection to Vagrant, so you might get strange SSH connection errors, which are apparently not due to your connection to the internet, but due to the antivirus blocking the local connection that your machine is trying to make from the Vagrant host to your virtual machine. For the Mac users, that was also a pretty brutal week for the Mac M1 users. But thanks to a bunch of students, particularly Zach, who figured out that you could emulate x86, we have a working solution. I put that, if you hadn't seen it, I put that on last week's notes, and I put a link to it. To it up here. So there's very specific instructions now for ARM-based Macs. So who has an ARM-based Mac that is not set up? Okay, have you tried setting it up? And it didn't work? Yeah. And following this didn't work? Okay, we'll have to, I guess, come to office hours. So just answer the assignment, say I'm still having trouble. If you didn't get it set up, and then we'll figure it out. Yeah.
I don't know if I'm completely done.
Say again?
I went through all those commands, but I don't know if that's all I need to do.
It should be. I mean, if at this point here you get the virtual machine prompt, like in the course, like in the lecture last time, which you can see what it looks like, then you should be fine. All right. So. Okay, I think we're doing pretty good, collectively at least, but I know for the few of you who are still having problems with the machines, that's, it doesn't matter if other people have done it. So yeah, we can use office hours next week, the TA today, and if there's time after the class today, I can help you try to work through these. Okay, so hopefully also in this class you'll see that software and computing is not just writing programs, writing algorithms. There's a whole ecosystem of installations, software, your programming environment. And this exercise is hopefully a little wake-up call that just even installing software is not so easy. And for maintainers of software, trying to support all the different machines, even for me, trying to support all the different operating systems and new machines that people have, it's kind of a nightmare. And it's a lot of what software is, software operations or software systems maintenance. Okay. Questions from last time. So last time we just went over the course, some kind of high-level ideas about the course, overview of what compilers are. Questions from last time? Okay. All right, so let's get started on today's material. Okay, so now almost everyone should have this, yeah.
I was just asking, explain the importance of the virtual machine and why we set it up specifically.
Why? So part of it is a selfish reason. I want to make grading easy. So if literally everyone has the same computer that you're working on, then, well, it's also not just for me, it's also for you guys. So because we're dealing with, because we're actually compiling to the hardware, compiling to the machine code, and our compiler needs to know about the specific development environment we're working on. So we need, you depend on which system you're on and which platform you're on. You may think you solved the problem, may work on your machine, but then we go to grade it. It doesn't work for some small reason. So as an example, I think several years ago, I think it was the Apple OS, or Mac OS, their compiler or their linker, something would initialize memory to 0 for you, whereas in the Linux world, it wouldn't. And so somebody had a bug where they somehow assumed that the initialization was 0 and it didn't trigger any error. But then when you went on a different machine, there was some trigger. You could see the bug. You could see a crash. Whereas on one machine, you wouldn't see the crash even though it was still a bug. And so cases like that are going to be very frustrating for all of us if we're trying to hit this moving target with lots of different machines. Because we're not just dealing, if you're using Python or Java, you are using a virtual machine. You're also using the same virtual machine, as long as you're using the same version of Java. But because we're actually dealing with the system and the hardware, I want to make sure that everyone has the exact same operating system, the exact same programming tools, the same development environment, and the exact same hardware. And so that's what virtualization provides. And in fact, in industry, the use of virtualization is done for this very same reason. So if you use, say, Amazon Web Services, you're not running on their bare hardware, you're running on a virtual machine. And they can provide a very consistent user experience. And whatever support tools they have for using their machines, using their services, they can write it once for their virtual machine. They don't have to, if say their provider, whoever's providing their data center hardware, updates to some new chip or updates to ARM for some reason, their virtualization should theoretically work as long as they can get the virtualization to work. Kind of make sense? And so especially nowadays, if you're going in an industry, virtualization I think is probably really common these days, having to kind of deal with it. And there's all sorts of tooling for configuring and deploying machines automatically, and a lot of automation. And Vagrant is one that apparently nobody uses anymore, but it's one virtualization automation. That Vagrant file configures your machine so that everyone has the same machine. But yeah, as long as you can get the virtualization software set up, then the machine you have on top of that is the same for everyone. But yeah, good question. You should ask why. Why bother doing this? Other questions from last time? Okay. It also makes this lecture much simpler because, well, simpler for me, because now that I know everyone has the exact same machine, the exact same operating system, I can teach you how to use this system. So the system I've given you has no windowing interface. There's no desktop setup. There's no Windows. There's no Mac. All you get is a command prompt. Has anyone ever played text adventure games? Okay, a small number of people. When I was younger, text adventure games were a little more modern at the time. You don't know what to do. It's just a text prompt, and you have to know the commands to run. The command prompt is kind of the same thing. There's a bit of a tough learning curve where if you're just dropped into it, like I've dropped you guys into an SSH prompt, a command prompt, you have no idea what to run, right? There's no built-in, well, there is built-in help, but you have to know the command to run the built-in help as well. And so today I just want to give an overview of how to use this command prompt. And as you learn this, and as you get better at using the command line, you'll discover that there's a lot more you can do with your machine. There's a lot more power that you have using your machine in a lot of ways, which I'll hopefully touch on and hopefully get across in this class. Basically, you're much closer to the system. You can use the specific parts of the operating system in a more fine-grained way using the command line. You're not trapped into whatever UI designer functionality they decided to provide for you. You have a much more flexible set of tools that you can use, and you can combine them in useful ways. Okay, so that's the pitch for why we do this. And I kind of just want to force everyone to do this. I feel like if you've graduated from computer science and you go to a company and they ask you to do something on the command line, or they ask you something about a system and you don't know that, I think it's going to be bad. I think the expectation is that you are comfortable on the command line, at least to some degree. There's also some software that just does not have a nice installation program or user interface, that they only provide you with instructions that you have to use the command line for. So having some basic understanding will help you, I think. It also gives you a better sense of how the actual operating system works, because you're forced to know the abstractions that the operating system gives you in order to use the command line. Okay, and so this is part of, I gave these 3 reasons, 3 things that I think all great programmers know, and one is knowing their tools. And that's what this lecture is about, is knowing the command line. Command line is this very powerful tool. We're going to cover the basic shell commands, so I'll probably use this interchangeably. Bash is the shell program. Shell is the name of the command line. It's some historical name. But if you hear command prompt, shell, command line, bash, effectively for this class, those are all synonyms. I may switch between them. We're going to look at navigating the file system, something that is increasingly obscured by operating systems today. We're going to look at processes, which are running programs. We're going to look at a bunch of useful utilities. I'm going to give you a little primer on using Git, which is what you have to use in order to submit software. So just like using virtualization in the command line, the version control is absolutely everywhere in industry for good reason. And using it on the command line exposes you to each individual command that Git provides, which a UI will not give you. So if you understand Git from the command line, you'll have no problem going to an interface. If you have an interface, you're a little trapped into how that designer exposed the Git commands to you. So just like learning how programming languages work will help you learn any programming language, I argue, learning the command line will help you be able to learn all sorts of tools that aren't even on the command line. Then we'll look at our compiler, GCC. We'll look at our make, which we'll use in the project for project management effectively, being able to do incremental compilation. And so if you do have Vagrant set up, follow along. You can open up your virtual machine and follow along with these commands. I'll give you guys a second to do this. And you don't have to follow along. The course, the lecture is being recorded, so you can always go back and watch it. I may go through it a little fast. Feel free to stop and ask questions. But it is recorded, so you can go back and pause and see what command it is, hand type it. I'm a strong believer in muscle memory, that programming is not just cerebral, it's also a little physical. If you're really good at algorithms, but you're very slow at typing, you're gonna have a hard time programming, right? Or maybe you can ask somebody else, a programmer, to do it for you. But it'll be slow when you first start doing this. But as you keep using the command line and as you keep using your system, you'll get faster over time. You don't necessarily have to know all the details of how these tools work. You can start learning idioms, start learning common patterns. I mean, that's what I do. I can't remember all of the commands, so I'll just Google it or go on Stack Overflow and find a command that somebody already figured out for me, and I'll just kind of practice it and use it over and over. All right, everyone have Vagrant up who would like to have Vagrant up? Anyone need more time? Okay, I'll give you a second. Oh, I need to get Vagrant up. I should probably use the virtual machine as well. All right, who cannot read this? Okay. All right, so let's get started with some of the basics. So by default, the command line prompt tells you your username, the name of the host name of the machine, colon is just a separator, and this little tilde here, at least in the default prompt, tells you your current directory. So in the Unix world, tilde is a shortcut for your home directory. So if we want to see what current directory you're in, we type pwd for print working directory. In the Unix world, typically the system is set up where all user home folders are in /home. / is the root folder. And if we want to get back to our home directory, then we type cd space the name of the directory. So in this case, I'll put tilde, and that'll just bring me back to the home directory. Whether there's a trailing slash or not doesn't matter, I don't think, for change directory. So if you're ever lost, if you're ever not sure of where you are in your file system, what folder you're in, pwd, print working directory, will tell you exactly where you are. This is especially useful if you're doing your editing on your Windows machine, for instance, and you have that folder mapped. So remember that the /vagrant folder is mapped to your host system's folder wherever you installed Vagrant, wherever your Vagrant file is. And so if you're ever lost and you're not sure where you are in your file system, print working directory. Everyone get that working? Okay. All right. And so if you want to see what files and directories you have in your current folder, ls. So let me go into. So I'm going to change direct. So this is probably what you'll do if you're using using the mapped folder. You'll change directory to /vagrant. And if you want to see what's in here, ls. ls for list, I think. Okay, so for instance, I've got my projects folder here. These are all of the templates. So if I'm now working on my toy compiler, you see that, so let me go a little slower. So if I'm in my /vagrant folder and I see that I've got a folder called projects, I can change directory into projects. And now you'll see that my command prompt is updated to tell me I'm now in /vagrant/projects. If I want to see what's in here, I type ls. And I'm going to continue to go to the first toy compiler. Okay, questions? All with me so far? Okay, so there's two ways to print things to the console. One is echo, which just writes them to standard output, which I'll talk about later, but it basically writes them to the console. So if you want to say something to write to the console, why would you ever want to do this? This seems kind of pointless, right? I mean, why would you need to text? Anyone have an idea of why you might want to use echo? Yeah.
Script.
Yeah, if you're writing your own script and you want to give information, it's basically printf for the command line. Okay, and so the other way to print something, another way to print something to the command line is cat. Now I don't know what cat is from, maybe concatenate, I don't really know. But cat will print the text context of a file. So if I say cat main.c, so notice here when I said list, ls, I saw that there was a file called main. And if I say cat and the name of the file, it will print the text contents of that file. So this is really useful on the command line just for exploring your file system. You don't need a mouse. So definitely using a windowed file system, Explorer is useful in some cases. But if you're just trying to navigate around quickly, trying to drag that mouse around and double click, it's going to be a lot slower for some cases. So I can very quickly go through my file system, look what files are there, just by using change directory cd, ls for list, cat, just to explore the file system that I have. Okay. So I talk about I/O a little bit more, but anything that I print out onto the command line, cat or echo, I can also redirect with this greater than sign to a new file. So I can create new files, text files, very easily on the command line. So I can make this new file.txt by using echo. So echo normally just prints to the console, but if I use this greater than sign, think of it like an arrow pointing to the file name, it will create, if it doesn't exist, overwrite the entire file, so be careful. It'll completely blow away your file. And it'll replace it'll add whatever output from the command I ran, in this case echo, it'll add that to put that in save that in the file. So how can I view this file that I just created? Cat, yeah, I can use cat. So if I say cat new file, voila, I've created a new file. Are you amazed that you can do this? Or does this seem really, really mundane? So I guess if you were doing this in like Windows or Mac, you'd have to like right-click, say like new file. It'll probably open it in Pages or something, type something. But in just a few seconds, I can create and destroy files at will. There's another command, tac, which is cat backwards, which will print out, well, that's not going to really apply to a file with one line. It'll print the file in reverse. I've actually used this. There are real cases that use this. Anyone think of a reason why you might want to use this? Okay. What's that? To see the bottom. Yeah, to see the bottom. Yeah, there are commands to see the bottom as well. So I don't know if I cover these, but there's something called tail. So tail will show. Oops, let me show main. So tail will show you the bottom. I think it's the bottom 20 lines. So it's not going to be very interesting. But I can say, show me the bottom 2 lines. But there are commands to do that. Okay, another way to view a file, especially if it's a long file. Let me see if I can find a long file here. Well, if my window were a lot smaller and I had a long file, I can use less. So there's an older command called more, and more will only print as much of the file as needed to fill your screen, and then you hit a key, like space, in order to see the rest, and it'll help you scroll through the file. So less is an improved version of more, and as a groan-worthy pun, the reason it's called less is because less is more. That's the stupid programmer joke. Okay, so with less, you can use like the arrow keys to go up and down. You won't be able to use your mouse. So if at any point you're in the command line, you're trying to use your mouse, you're going to get very frustrated because all it's going to do is like highlight stuff. And the mouse will have no interaction with the command line. But with less, you can explore the text file by scrolling up and down. You can use the arrow keys. And because it's not like easily self-documenting, people are like, students are always like, well, how do I get out of here? You hit Q to quit. So you would never know that, right? There's nothing on the interface that tells you to do that, but Q to quit for less. Okay, questions so far? Everyone following along? Okay, so that's how we can explore our file system, create files, destroy files, print them. Or actually, I haven't told you how to destroy them yet, but. All right, you can do other things like make directories. So I can make a new directory here called new dir. And when I list my folder contents, you can see here's the new directory. And it's actually doing some color coding. My shell is set to do some color coding to distinguish between directories. Okay, so I can use cd, change directory, to go into this directory. ls to list, there are no files in here, apparently. If I want to go back to the parent directory, there are actually two special directories in every folder. One is dot, just a dot by itself, and that's a reference to the current folder. And one is double dot, that's a reference to the parent folder. So if you're wondering, well, how do I navigate back to the parent folder? Do I have to just like type in the full path again? You don't, so you can just write cd space dot dot. You might have seen this in Windows. And that will, you can see that my prompt has updated from new deer back to the parent folder, toy1. If you want to create a file without putting any contents in it, you just want the file to be created, you can use the touch command. So I'm just going to touch empty file. When I go to print it, what should I see? Nothing. And if I type ls, I can see that there is a file here. It has no, it's empty. Okay, so let me show you how to remove a directory. So there's a command called rm for remove, dir. And you put the name of the directory. But we get this message. It says, failed to remove new directory, directory not empty. So either, well, you could argue it's safety reasons or because these commands are very low level. Remove directory is just removing the directory. It's not actually deleting the contents of the directory. And so to make sure you don't have a bunch of files that are created where there's no way to access them through the file system, remove directory will check to make sure the directory is empty first. So to remove a file, the rm command will remove a file. It's not recoverable within the file system, at least. You might be able to look at the raw bytes of your drive and recover it, but you'll no longer have access to this through your system. You don't have to change directory to touch or edit files in a subdirectory or any other directory. You can just put the path to the file. So here, I'm saying remove new directory. New dir is the subdirectory that contains empty file folder. / separates directory names from other directories or file names. So if I type rm new directory empty file, oops, you'll see that now this new directory is empty. And if I run remove dir now, I can remove the directory. And I can confirm that by running ls, and you can see that new dir is not here anymore. Questions? Yeah? So touch just creates an empty file. All right, so let me show you how to move and rename files. So let's make a new directory here. Target directory. I didn't use that. Let's copy this new file to target. Oh yeah, so I forgot about copy. So copying files. So if you want to duplicate the file, use the cp command for copy. The first argument is the name of the file or the path to the file. And the second argument is the directory, the path to the directory. So if I write copy, you'll see that in my current directory, toy1, I've got a new file. And if I list my target directory, you'll see I also have a new file. So even though the contents will be identical when you copy them, they're not the same file. So if I print the contents of new file in my current directory and I print the contents of new file in my target directory, the contents are now the same. But I could overwrite or add to the contents. Double arrow will append to the file instead of overwriting it. So if I write to new file, and then I run the command, let's say I run the command target dir new file.txt. What will be output when I run this cat command? Will it be hello world or will it be hello world, hello again? Who says it'll just be hello world by itself? Who says it'll be hello world with hello again afterwards? Okay, I forget which one is right, so let's see. So it's just hello world. So I edited the file in my current directory, which is toy1. I'm sorry, yeah, I edited the file in my current directory, which is toy1. I'm even confusing myself here. But I printed the copy of that file that I made earlier in target dir. So they have the same name, but they're in different directories, and they're different files. Okay, so if I print out the new file in my current directory, should I get hello world by itself? Raise your hand. Or should I get hello world with hello again afterwards? Okay, good. And that's exactly what we expect. So there are ways to actually have the same exact file in different directories. They're called links, hard links and soft links. I won't go into that. There's a command called ln for doing that if you really want to do that. You can do that. You can make a graph instead of a directory tree. Okay, so in contrast, move will not copy the file, it'll move the file. So let me create another new file here. So move example. So here I'm using echo to create a new file. You can see, here's move example. And now the move command is mv. So let me move, move this example to the target directory. After I run that, you'll notice that in my current directory, move example doesn't exist. But if I list the target directory, you see move example is now here. Let me show that again since it didn't actually list my current directory. So this is one reason why there is a dot directory to refer to the current directory. So for instance, if you want to move something to the current directory from somewhere else, you don't have a way to reference it without typing the full path. So this dot directory is always a reference to the current folder. So I can move this file from target directory back to the current directory with this command, mv for move, the path to the file, and then the path that I want to move it to, the target path. If I list the target directory, you'll see move example is now gone. But in my current folder, move example is there. Questions? Yeah.
What's the difference between the single arrow and the double arrows and arrow?
Oh, yeah. So single arrow will rewrite the entire file. So if I do a single arrow to new file, it's going to blow away the entire file. If I do double arrows, it will append to the file. So now if I cat, you'll see I have, it didn't blow away the whole file. There's another command called trunk, which will just blow away the file. Oh, what's it called? Oh, truncate, no, it's called truncate. Oh, all right, so, really? Okay, so you can truncate it to file. Yeah, you can truncate it to any length you want. So I guess what I could have done is say truncate, I don't know, to size 5. So it actually like took off it allowed the only first 5 characters, I guess. I guess EOF is a file. Anyway, don't need to worry, you probably don't need to use that. All right, other questions? It might also be useful to list not only the current folder, but also all subdirectories. So you can use -R to list both the current directory and it'll go through all subdirectories. There's another command called tree that I think will do something similar, although I don't even have it installed. But you can use ls-R if you want to see the whole file tree. So I'm going to go back to my parent here and run -R, and you'll see that ls-R it'll give me the listing of every folder and its subfolders, and it'll do it recursively. So it printed out simple C4, printed out simple C4/tests. Might be useful. All right, questions? Thoughts? Is this review for some people? Is this new for some people? Okay, good. All right, so even though for people it's not new to, hopefully, there'll be some trick in here that you haven't seen. All right, so for using the command line, I think Windows has this as well. This is probably like the most important takeaway. If you take away anything from this, using the command line, it's tab completion. This is what makes using the command line tolerable. Probably up to this point, you've been typing everything out one at a time, and it's really slow, and you're like, by hoping I'll slow down so you'll catch up. I'm not typing every command out, and the reason is because there's this incredibly useful functionality in the shell called tab completion. So let me show you what that looks like. Let me go back into my toy directory, and let's go back into this target directory. Okay, so let's say I wanted to I wanted to print out this new file. Now, without tab completion, I would have to type each character one at a time. Very slow. So instead, all I have to do with tab completion is to start writing the name of the file or the directory and just hit the tab key. I'm just literally hitting tab, and like magic, it completes the whole file name for me. The most useful feature that makes using the command line fast and tolerable. If you had to type everything out, it would be rough. Just hit tab. This also works for commands themselves. So if I type C and start hitting tab, it'll give me all the commands that start with C. If I type CA, it'll give me all the commands that start with CA, and you see cat is there. Okay, but what if I have another file that also starts with N? I kind of previewed this a little bit. So if I type N and hit tab, instead of completing for me if there are multiple options, it'll give you all the files that have the same prefix that you typed. And so not only does it do completion for you, it also helps you explore your file system automatically. So just by hitting tab over and over, it'll just say, hey, I can't figure out which one to complete with, so give me more information. So as soon as I type E and hit tab, it can disambiguate between the two files. So you don't need to type out the entire new file, you just need to type the unique prefix of whatever file or folder that you're trying to type out. Hit tab, and voila. That's how I was able to, it looks like I'm typing fast, but I'm not. I'm using tab completion aggressively. So the most useful tool for any command line user, I argue. Who's seen tab completion before? I'm just curious. So not that many, okay. All right, so that'll make using this command line much more tolerable and much faster for you. So if you forget everything from today, remember tab completion. Okay, so let me review just the directory hierarchy stuff. I kind of covered it a little bit. So in the Unix, Linux world, unlike in Windows where you have C drive, D drive, each storage device or whatever storage device you have is given a unique drive letter. In the Unix world, the entire file system with all of the storage devices, and in fact, all of the hardware, more or less, is all in one single file system tree. And the root of that file system tree is the / by itself. So if I type ls /, this is the entire file system, including all hard drives I may have attached to the system, including all shared folders. So for instance, the Vagrant folder was mapped to my host system. It's not part of the, if this were a physical machine, it would not be on the SSD that I'm running. It would actually be, the file system would have to go out to the network to go access that shared drive. And so you can really access every device, every piece of hardware, pretty much technically, in a Unix system from the root of the file system. So that's why there is this dev folder, which are special files. They're not files like in the file system that store data. They map to other parts of the hardware. Yeah?
Would you be able to remove directly folders and stuff?
Yeah, I don't think so. I don't want to try it. I mean, it'll probably just remove all the contents of it, but not remove / itself. Can you remove /? Yeah, I don't think so. I think it's probably baked in. Anyone else? No? Different answer?
If you were to do
// yeah. But I don't think it would remove / itself, right? / would still be there. Yeah?
Is there a way of displaying all files on the system and creating subfolders?
Yeah, so that's ls-R. So if I say ls-R, but I give the root, then it will print everything in the system. So yeah, back to your comment about remove. So this is some trick that people on the internet used to convince naive internet users to do. So I'm going to comment it out just in case I hit enter. So this will, I don't know if it's / or star. So remove, I mean, don't do this, but dash R, it says recursively remove. So actually, I can show an example of this if I want to delete this target directory, if it's got other subdirectories in it and other files. I can show you what my, just like your colleague just asked, I can show you the entire subtree with ls-r, and you see that there are 2 folders, one nested inside each other. I can't use rmdir because it's not empty. But I can recursively remove everything in target dir. I always do F because I think it's going to ask me, but oh no, it won't actually. So I just blew away the entire target directory file structure. The target directory is gone, as well as every file, every directory under it, every subdirectory. It's all gone. I mean, it's probably somewhere in some bits on the hard drive, but it's inaccessible now from your file system. So if you can imagine if you were to do that on the root, you just delete every file in your system that you have permission to delete. Yeah? Oh, I don't, that's a good question. So directories are actually files. So this is the Unix philosophy, is that everything is a file. Directories themselves are also technically files. I can't remember how to show the file, but it's a special file that basically has pointers to all of the files and folders in its directory. So let's see what happens if we try to truncate it. I'm guessing it'll check if it's a file directory. If we did that, it would be effectively deleting the contents of it because we would do the same thing. Yeah, so it doesn't allow you, yeah, so you can't write to directory files. The file system itself is managing, it's a special file that basically just contains a pointer to the other files, but the file system is managing it, and the command line tools will restrict you from doing it, or the file system itself will restrict you from doing it. But that's an interesting question. But yeah, just in the Unix philosophy, directories themselves are also files. They're special files. Okay, so everything starts at root. In my root folder, I have, so yeah, as I mentioned, we have the contents of our hard drive. So yeah, I mean, without going too much into like the Unix system management, bin, etc, home, lib, these are all folders that are usually on a hard drive, often on the same hard drive. Home may be on a separate hard drive. Boot is often in a different partition. Dev are also not real files in the sense that they contain binary data on a storage medium. They allow you to access hardware directly. So I think you can even access like memory and things like this. So this is like if you wanted to access the physical RAM and just start like changing bits on the physical RAM, you can actually do this treating it just as a file. So you know, technically you'd be able to say like cat some file or echo hello world and just like start messing with your memory. Now Unix also has a permission system, thankfully, to make sure that random users can't just like touch hardware. But yeah, technically you could. If I ran this with sudo, I'd probably start breaking stuff. Yeah?
What do the different colors mean?
I don't know, actually, in this case. So let's see. So -L will give you more information about files. So it'll give me a listing like this. So blue is a directory. This D means a directory. C, I guess it's like some, I guess that's like a device file. Yeah, I guess that's all what it is. So the blue ones are, dark blue are directories. These are links. I was telling you that you could have a directory graph instead of a directory tree. So this file actually points to a different file in your file system. I don't know what highlighted means. Oh, T. I don't know what that means. So if you ever forget how to use a command, you can use man. So I'm gonna, well, yeah, this is gonna be complicated to look through. So this will probably tell you what all of the what all the output means. But the color coding is like the different types of files, whether they're special files like directories or device files, whether they're links. But this is all like superficial. This is all the bash program that's doing this for you. Good question. Other questions? Okay. Okay, so let me finish up the directory hierarchy stuff. As I mentioned, you can see the current directory with pwd. You can change directory. So also because they have this notion of a root file system, any paths that start with slash are absolute paths. You give the entire name starting from the root with every subdirectory to that folder. If you omit the / and just say, for instance here I just say vagrant, it's a relative path, relative to your current directory. So whatever files and folders are in your current directory, if you omit the / and run some command on them like cat, and I want to output, say, the vagrant file, it'll be relative to your current directory, current working directory. So for instance, if I'm in another part of my file system, like here I'm in my home folder, I'm nowhere near my vagrant folder. If I want to print out that vagrant file again, I can start with / and provide the full path, every subdirectory, to reach that file. So I'm using tab completion here to help me go through this, but I can I can specify the full path anywhere in any working directory. It'll ignore the current working directory and just give you the full path starting from root. So let me actually, another thing that I probably should have mentioned along with tab completion that also makes this really easier. Using the up arrow or Control-P, Control-N, using the up and down arrow will give you past commands. So there's another thing that if you take anything away and you have to like rerun your compiler or rerun a test, you don't have to type it out again. You can just hit the up arrow to give you the last command, and it'll give you the whole history. And if you want to get really fancy, Control-R will allow you to search your history, and it'll fill in with whatever matches as you type. So if I've typed cat, it'll match the most recent last command that I ran. If I keep typing Control-R again, it'll cycle backwards through all of the commands that matched whatever I typed. So you can see the whole history of what I was running. So tab completion and using the up arrow to get to past commands. If you remember that and nothing else, the command line will be tolerable. It won't be so frustrating to use. Okay, so I'm just going to go back to this directory here with change directory. Just to review, the special folders that are in every folder, every directory are dot for the current directory. So if I say ls dot versus just ls, I get the same contents because dot is the current folder. Dot dot is the parent folder. So if I do ls or change directory, it refers to the parent folder. And because we always have this special directory called dot that references the current directory, running cat on new file is the same as running cat / new file. So because dot always refers to the current folder, I can have a relative path that just always refers to the current folder. And so actually I think I can do this because it's just always referring to the current folder. So I say go to the current folder, then look at that folder's current folder, then look at that folder's current folder, look at that folder's current folder. And then I have this ls-la. This is something I run often. I often do ls-this. I just do this all the time whenever I'm navigating because it gives me the most recently edited file. But ls-la is a common thing to use to see the types of files. Yeah. Yeah, that's exactly right. Yeah, probably something I should have mentioned. So if you do .. that's going to refer to the parent. Yeah, very good question. That's going to refer to the parent projects, I can say dot dot slash again to refer to its parent, which is Vagrant. And so when I run ls, that's going to give me the same contents as if I ran, the full path to Vagrant here. Good question. I probably should have that in my notes. Yeah.
So what is dot slash you can read forward?
So dot is the current folder. And so if I say dot again, it just says the current folder again. And then the current folder of the current folder, the current folder again. Does that kind of make sense? It's just referring to itself each time. It's always referring to itself. I mean, nobody would ever write that, but because like inside of every directory, so for instance, if I were to, so let me go back to the root, and I want to list the toy1 directory using its absolute path. That's the contents I get. What ls is hiding from you is that there are two, so to go into a little more, any files that start with a dot are hidden by the shell. Windows has hidden files, Mac has hidden files. It's just a convention. Using -a for all, you can think of all, will show you all the files, including the hidden files. These two special directories that are in every directory are hidden files. And you can see also the Git repository is actually a hidden file inside of your folder. It's not the contents of your folder. It's actually the contents of the Git folder. So if I were so that special directory there, that dot directory, just like dot dot is a reference to the parent. So you can see here that if I do ls-a, the full path to toy, and then say dot dot, that will give me what folder, what directory will that give me? If I say Vagrant projects toy1 and then dot dot, yeah. Yeah, it gives me Vagrant projects because the dot dot folder, whenever you refer to it from any folder, will give you the parent. So you can see here, here's the dot dot folder. By the same token, if I refer to the dot folder, dot directory, it'll give me the current directory that I'm in. So if I say Vagrant projects toy1 and then dot, what folder or what directory is going to be listed? What's that? Toy1, yeah, it'll be toy1. And now that's a reference to the toy1 directory. So if I say dot again and want to list Vagrant projects toy1 and then the dot directory and then its dot directory, what directory am I going to be listing? Toy1 again. So I mean, using it for this purpose is kind of unnecessary. But it is useful when you need to refer to your current directory, like when you're moving a file. Has anyone ever had to do this? ./a.out, you probably had to do that. You probably wondered why you had to do that. The reason why is because, this helps explain it, is that when any executables, they'll only be, so you can only execute programs that are in a predefined set of directories that you've told the system to allow you to run programs from. This will help avoid, people accidentally blowing away your system or having duplicate names. So basically, there's a predefined set of directories that you're allowed to run programs from. It'll basically, whenever you write a command, say cat, for instance, the shell will look in these directories and say, where's the cat command? You can actually ask which directory it's in by saying which, and it'll tell me which directory. It will give me the full path to the command. But if you say make your own program, your own executable, it's probably not going to be in that path. But if you give the full path to the program, then it will run it. So I could say, actually I should probably have a program to run, but well, let's pretend I just built the cat program. So here's my cat program. If I just built it myself and it weren't in the path, and I ran a.out, it would say I can't find this. What would it say? It would say like command not found. So if I say /, I'm giving the full path to that program, and then you can execute things if you give the full path to them. It's just that by default, Bash will only execute programs without a path that exist in those directories, those predefined directories. This is all just a convention. This is all design. There's nothing like theoretically true or fundamentally natural about this. These are design decisions. Okay, questions? Okay, so I said quite a bit about redirection already, but let me say a few more things about redirection. So as I said before, you can use this arrow to save the output of anything that you run. So instead of ls printing out to the console, I save it to a file with that redirect command, and now I can use cat to print it out. All right, yeah, I think I have time to do this. All right, so let me make a quick program here. Hopefully this builds. So just to illustrate what I showed before, I have this program called printer. It says command not pound, but if I put the slash before it, I've given the shell the full path to the program to run. Okay, so I've used these mysterious fprintf commands. Who's used fprintf before? Because it tells, you print to a specific file, right? It allows you to print to a specific file. So in the Unix world, there are 3 files that every program is given when it starts up. There's standard input, standard output, and standard error output. And these are like basically given to you by the system. So whenever you use fprintf, these 3 files exist already, or scanf. And in fact, when you run printf by itself, it's equivalent to running fprintf standard out. So in the shell sets up all processes that you run to have standard in coming from the console, coming from the keyboard. So if I say cat without any file, it's going to take whatever input I write on the console and print it out. So it's just like repeating. It's like repeating whatever I say. So it's reading in from my whatever I'm typing, and it's writing out to the console. So standard in and standard out are always given by the system, and it's up to whoever executes that program, in this case the shell, to set up what actual files they should be. So remember, on Unix, files are not just files on storage. They could be hardware as well. So in this case, my console is a kind of virtual kind of hardware, and standard in and standard out are being set to my console input and output. So this is why we can also say something like this. I could write a program like this, for instance, by taking advantage of the fact that when I run cat, by default it's using standard in, and I can use the redirect command to change standard out to write to a file, and I can write my program right in the console without actually opening up an editor or anything. And so if I actually print out the file, you'll see it's exactly what I typed on the command line, and I can actually just like build this. Yeah, complains about not having, but it runs. Okay, so back to this program that I just wrote. This is all just the design of the Unix system. There are 2 output files. One is the standard out, one is the standard error. This is just a convention. Programs will write what's supposed to be the main output of the program to standard out, and it'll write error output, error messages to standard error. So why would you want to do this? you can save the output separately. You can save them to two different files. So for instance, so yeah, let me illustrate this with the printer command. So it looks like they're all being printed at the same place, printed to my console. But in fact, both files are just being set to the console. And I can illustrate that by writing the output of printer, redirecting it with this arrow command to a file called out. And you'll see when I run it, I only get this standard error output. So it's taken the standard out output, saved it to the out file. You can see I can print out the out file, and you can see standard output being written there. And it wrote standard error to the console output. If I want to redirect the standard error output, I can use this redirect command to arrow. So it's telling you which, this is like the file identifier. And so you see nothing comes to the console because I've redirected the output from both standard error and standard out to two different files, out and error. And you can confirm that by actually printing out the two files separately. So there's standard error output, and here's standard out output. Yeah?
Why don't you have to do like out Like, what's the requirement?
Oh, yeah, so that's another thing that the sort of windowing interface, this is also like kind of a convention. There's nothing, at least in the Unix operating system, and probably even Windows, where the extension has any meaning for the file system. I think Mac OS may build in some meaning to extensions, but yeah, extensions are just, they're just part of the name, they're just a convention. So there's nothing about the extension that stops the system from using the file in any way that it wants. This is actually, I think, one of the reasons why there are like phishing attacks that will send you a file. It'll be like, you won $1 million.txt, and the operating systems hide extensions as a convenience, but it may actually be like .txt.exe, and it'll look like it's a .txt file and be like, oh, let me look at my winning code, and then you'll double click on it, it'll run a program, and then you're owned, your machine's owned. Yeah.
So how do you actually file editing view again?
File editing view?
Yeah.
You mean less or Emacs?
Right here.
Oh, you're in Emacs. Oh, sorry. I probably should not have used Emacs to do this. It's Control X, Control C to get out. Sorry about that. I should have just done it on the command line. Okay, and last thing is that if you want to redirect both of these to the same place, you use this little command here, or this little redirect syntax here that says redirect the standard out to, redirect the standard error to the standard out. Anyway, you're probably not going to have to worry about this. So, oh man, okay. All right, so redirection works not only between programs and files, it also works between programs. So this is one of the most powerful parts of the Unix command line and the Unix philosophy, is that you can link together multiple programs and have a pipeline of data processing. So let me show an example of this. So for instance, I want to search a file for some contents. So let's take this, let's take this hello program. So you know that cat now will print out, it'll print out the text of a file. So another way to say it is that cat is taking a file and writing it to the standard out. Instead of arrow, if I use pipe, the vertical bar, it'll take the output of the first command and redirect it to the input of the next command. So if I run grep by itself, grep is just a file search, a text search. If I grep for the word hello, it just seems like it's freezing. It's waiting for input from the user on the console. So if I just type random stuff and embed a little hello in there, grep is going to identify the line, and at least with this settings, it'll highlight where that, so it's, REP stands for regular expressions. I guess global, I don't know what it is. It stands for regular expression. So it's searching for whatever text you gave in the file that you've provided. But if I type without hello, it doesn't say anything. So grep by default just reads text from its standard in and writes to its standard out. So I can link together the output from the cat command to the input of grep. And so now instead of waiting for the user to give text for standard in for grep is coming from the output of cat. So what do you think should happen when I run this command? Just as a guess, yeah. Okay, so your colleague is saying it'll print the line of my C file. So let me show you my C file. This is my C file, and it'll print, even though you just saw grep just now, it'll find the line on which all hellos occur, and at least with this configuration, it'll highlight that word. So instead of like going to your Finder or your macOS search bar and typing in some text and hoping it's indexed, you can quite literally search files in a very controlled way on the command line. Yeah?
I just wanted to say that the last argument.
Yeah. So that's right. So grep also takes arguments. So this is kind of a common thing in Unix tools. If, for instance, cat will also take standard in, but you can give a file. So there's a little logic that'll say, if you've given a file name, use that as your input. If you don't have it, then use standard in by default. This is all just kind of design decisions from, yeah. Yes, yeah, yes. It is case sensitive. So there is a way to make it not case sensitive. So that's a good question. So yeah, in general, in the Unix world, yeah, the capitalized version and the lowercase version are two different characters. They're two different character codes, and these tools are case sensitive. Okay, so if I were to say, just to illustrate this, if I were to search for all caps hello, then it's not going to find anything. But grep has a command -I, I think, for ignore case, that will ignore the case if you want to use that. No problem. Other questions? Oh yeah, yeah. I mean, I think this is automated. What do you mean? What do you mean automated?
Like, if you were to have a file that had a bunch of commands that allowed you, like, let's say you have 7 files and you put the input into the first file and you want the output of the last file. Meanwhile, all the other files are automated just through putting one input.
Oh, there are like for loops in shells. You could also generate the bash command. So you want to generate like 7 pipes in a row based on files. You can do that. if you want to explore more, let me know. This is more advanced shell scripting, but yeah, you can do stuff like that. I would probably generate the command, use a for loop to generate the command, and then you can actually pipe to bash to have it run. So I can like echo cat. This is a bit of well, I tend to go on tangents, so this is one quick tangent. So I can actually echo the command cat hello, pipe it to bash. So the output of echo is cat hello. Pipe it to the bash command, which is my shell, and it'll run the command. So don't worry about that if this is getting a little mind warpy, I guess. But yeah, you can do that. Okay, so yeah, okay, so let me let's see. Let me go through one more thing, and then yeah, it's been about an hour and 15 minutes. So, all right. So PS will tell you your running processes, so you can see I still have Emacs running. You can actually kill processes this way. So if I just wanted to kill Emacs, you can end processes this way. PS stands for processes. I have to kill it a little more aggressively. So you can see here, there's only 2 programs running when I type PS, my shell program and the PS program itself. If I want to see the whole system, this is just the thing I memorized. I don't remember what it all stands for. I can pipe this to less. So if this goes off the screen, there's like a lot of content here. This is where using less is really useful. If you have output that's too big for your screen, pipe it to less. And now I can use the arrow keys and page up and page down and other shortcuts to explore this file. So this is every process running, every program running on your machine. Yeah, in your whole machine. The first command is, or the first thing is the user that's running it. So a lot of this is root. And I can show you here how I can find all of the programs that my user, Paul, is running. Actually, in this case, it would be Vagrant. My user, Vagrant, is running on this machine. So PS will only show your local shell what programs are running. So there's another example of using pipe, where you can take the output of one command and pipe it to the input of another. grep, I use grep. I do this stuff all the time when I'm like actually doing research and running stuff. Top will also show you running commands, running programs, and their CPU usage. HTOP, which I don't think is installed. Oh, it is installed. HTOP is just a more fancy version of this. Yeah. All right, so it's been almost an hour and a half, so I think maybe we should take a break at this point. Let's keep it to a 10-minute break. So let's say come back at 11:05. And yeah, let's leave it there for now.
So,
All right, welcome back, everyone. Let's finish up with the command line tutorial. Then we'll go over Git and a little overview of how source code actually gets executed. Okay, so there's not much more to talk about on the command line. There's one command. Oh, can't see that. There's one command called man for a manual page that if you know the command like grep and you forget, for instance, how to ignore case, you can run man grep and you can scroll through this file. So it's basically using the less command. So if you want to get out, hit Q to quit. It actually tells you at the bottom, unfortunately, in this version of it. Hit Q to quit. It has documentation for like C libraries. So if you type the name of a C program, it'll show you the documentation for it. Sometimes a command is both a shell command and a library call. So if you do -A, it'll show you all the documentation it has for the different sets of documentation. Actually, not like Signal, for instance. So when you quit, it'll just like go through all of the pages it has about Signal. Okay, I don't think we need to go to tar. This is like basically like zip files if you want to package files. I said I would talk about editors, so I opened up Emacs and I forgot to actually tell people what I was doing. Emacs is a famous sort of Emacs versus Vim online, internet arguments about which one is better. They both have kind of steep learning curves. The easiest editor to use on a command line is called Nano, because it takes the arrow commands and it tells you how to exit and save. So if you want to do like quick editing on the command line, you can use this. This little caret means control, the control key. So hold control and hit X to exit. It'll ask you whether you want to save it, yes or no. I'll save it. It'll ask me the file. By default, it'll be the current file. So this is just if you want to do editing on the command line, this is an easy way to get into it. But hopefully, if you've got the Vagrant folder mapped to your host machine, then you won't have to you can edit on your host machine. So there are other commands that we don't really have to go into that much. So there's like diff will show you all the lines that differ in the left and right file. OD shows you the raw bytes. So this shows you the raw bytes of a file. wget and curl are useful if you did the M1 Mac instructions. You can actually download files this way. So I can download this HTML file from the internet. And now I've got this O2 tools HTML. So wget and the name and the URL, or curl. Curl will just write it to standard out. You can see here I ran curl and a web page. Oh yeah, also this is kind of useful for Windows users. Oh, these have to be installed, don't they? I don't remember where these are. So. So hopefully this won't be an issue for most people. There's a utility that'll convert between Windows and Unix text files. You might see, let's see. If you open up your editor, you might, well, it doesn't even have it here. Well, anyway, you might have issues with like Git. I can't remember why I have this in here. I think people in Windows had issues with their files having like extra endings to them, this /r/n. So on Windows, like, you know, yeah.
Bash scripts don't like the other side.
The bash, okay, so it might be the bash script. So if you're saving stuff in Windows, like, you know how when you run hello world, you have to do /n for a new line? Historically on Windows systems, DOS systems, they, instead of doing /n, they do /r/n, which is character return. And so all these utilities do, they basically convert between /r/n and just /n. So you can see when I converted it to a DOS file, it added /r/n. When I converted it back to Unix, it just is /n. This is something that it won't be an issue. You'll know if it's an issue. It'll come up. Hopefully it won't be an issue. Yeah, for Windows users, this might be an issue. You can let me know, and I'll give more details on it. Okay, so let me get into the Git tutorial. So this will show you how to actually submit your projects. And let me get to the all right, so on the home screen of web courses, I've put the GitHub Classroom links that will automatically create Git repositories for you. This first one is a Git sandbox. This is not graded or anything. This is just to get you to practice using this way of doing stuff. So it'll ask you to accept the assignment. So you'll see a page like this, accept the assignment. It will take a minute to set up the repository, and then eventually you should see a link to your repository. So if you go to this link, you'll see a page like this where it's just a completely empty Git repository. So in order to add this, you can just follow the directions here to create a new repository. So I'm just gonna create a README. Oops, So I think for the other projects, yeah, I probably should have set up with a README, but for the other projects, it'll be a template, so you won't have to create the repository yourself, but it's kind of useful to go through to see how the command line process works with Git. So with Git, to create a new repository, you could take a new folder or any folder you want, create an empty repository. You can add files with git add. Let's make our first commit. do my online. I think I'm going to have to do this in my host machine for now. Wait. Oh, I see. Right, so I guess it's because GitHub changed the default to main. Oh yeah, sorry, I don't have this set up. All right, let me cover that with the toy one later because it doesn't require making a new repository. Let me just go over the. I'll just follow my notes instead of doing it this way. All right, I'm going to start with the toy compiler, since I apparently can't. What am I doing wrong? Sorry, I'm just wondering why. All right, let me try this again. Okay, so I think because my Vagrant machine was not set up with keys, and that was actually the first thing on my notes to describe, was how do you set up Git so that you don't have to type in your username and password every time you use it. So when you use Git, so who's used Git before? Who's never used Git? Okay. Was it in class? Was it class? Okay, that's good. Yeah, several years ago there was, Git was new to people when they came here. So who has set up their SSH keys for Git? Who has not done that? Who types their username and password every time they do push or pull? Oh. For those of you who have not set up their SSH keys, how do you avoid not typing your username and password every time? Yeah?
You can either use a virtual access tokens or environmental variable.
Environment, oh. So you put your password in an environment variable?
Yep.
That's not a great idea. So it's just in plain text. Yeah, you might not want to do that. The tokens, that's probably your SSH key, I'm guessing. So to do that on the command line, well, actually, I can go back into Vagrant to do this. So I don't want to go into my account and like add a key or anything, but I will show you how to make the key, and then there are directions on GitHub to show you how to tell GitHub what that key is. So these, so we make a new key. I think I like to add more bits. So you can just save the key to whatever default directory they have in your, so I'm in my virtual machine. Adding a passphrase is a good idea in general. In your virtual machine, maybe, maybe not. I'm gonna leave it empty. But you're gonna add this to GitHub, so whoever has this key will be able to make changes to any of your GitHub repositories. So now you know the public fingerprint of my key. Do I have this tool keychain? So there's this useful tool that I use called Keychain, which will make it so you don't have to put in the password for your key all the time. It'll save your key in memory with a timeout. Use SSH add to have this key housed in memory for you. And then if you want GitHub to be able to recognize this key whenever you use Git to push and pull stuff, you'll need the public key here. So don't send this. This is your private key. Anyone who has access to this number will be able to impersonate you on GitHub. Send the public key. So you can view the public key here using cat to print out the text of the public key. And then there are directions here for, there are directions here for like doing this whole process. It'll show you where in the GitHub menus you go to settings, SSH keys, you add a new SSH key, and you copy in this pub file, the text of the pub file, and then voila, you can say git push and pull. You don't need to expose your password in an environment variable or in a text file or however you're doing it. And you don't need to type your username and password every time. And instead of using the HTTPS, so if you clone this one, GitHub, the Git is going to ask you for your username and password every time. There are ways to save that as well, actually. But if you have your SSH keys, you can use this link to set as the remote for your repository, and then you can push and pull without a username and password. It'll use that key to authenticate you to GitHub. Yeah?
Does it work if you have two-factor authentication?
I think so, yeah. Yeah, it does, it does. It does work with that. Yeah, the keys, yeah, it does. Yeah, because I have two-factor, and I use this. I use this all the time. Yeah, so it does. I guess the idea is you can add and remove those SSH keys, and hopefully you're managing them safely. That's why you should also put a password on your SSH key as well, because it will provide. So it won't provide access to the interface of GitHub, but it will provide access to push and pull to your repositories. You can probably do some damage with that. All right, so I strongly recommend doing this this process here in your Vagrant machine to make yourself a new key, add it to GitHub. In order to start committing stuff to your repository, you can set up your name and your school email address or whatever email address you want. This is going to be used only for the repository. Okay, so because I have this set up in my my host machine, I'm going to do the rest of this process in my host machine. So sorry for making that a little scattered, but I created this new repository. I copied these commands in order to create the repository. And as long as you added your SSH key in Vagrant, or created it in Vagrant and added it in GitHub, this push command should work. So if I refresh this page, you can see that after I pushed, I now have this README here. Questions about this? I know I kind of jumped around a little bit. Yeah. I don't know. Let's see. So where was that command? It was here, right? So you can look at the man page for git branch, or I can look at it. Search for -n. So it says old branch will be renamed. If it's uppercase, it forces. Oh, okay. So it'll force it to be renamed. Oh, I see. So if the new branch exists already, I guess, so you can overwrite the new branch, I guess. Yeah.
If you're running out on your Vagrant machine, do you still need the same SSH key?
GitHub will allow you to enter I think as many SSH keys as you want. So you can have like one per machine. This is like key management design. Yeah, you can add as many as you want. So you can have one for Vagrant, one for your host machine, one for however much you use. And then after the class, you can delete the Vagrant key and delete your Vagrant machine, so that you don't have any backdoors into your account. Okay, so let me walk through that one more time. What I did, since I kind of jumped around doing this, and actually I can probably delete this repository. So it tries to make sure you, oh, not that repository. I mean, I guess it doesn't matter, but. Oh, I need two-factor. All right, forget it. So anyway, you just click on this link. You go to accept the repository. It's going to give you that screen where it says you have to set it up for the first time. Just cut and paste those commands to your virtual machine, and it'll set it up. You can follow the directions for adding the SSH key. It's in GitHub as well. They give you nice directions. I've also given you commands here. I mean, they do something similar. So I highly recommend the SSH key. Follow the directions here, and then you can set up your Git scratch in order to experiment with Git. Okay, so questions on that? So I know that was a little scattered, but questions? Okay, so let's take a look at how to use Git. So one of the most useful commands is git status. It'll tell you whether any changes you've made in your current directory, your working tree, differs from the repository that you've committed, that you've saved. Another really important command is git log. This shows you the history of all the changes that you've made. And you can even view what the change was by saying git show. So git show will give you the most recent commit that you made. So here's the commit log and commit information that we saw in the log. And all commits are just diffs. They take the current state of the repository and they take the diff between any changes you made. So for instance, if I edit this README, and now I'm on my machine, so I can actually edit it in a window. So I make some change to the code in my repository. Git status will tell me that there are some files that have been modified compared to the current state of the repository. And I can view the differences by running git diff. So git diff will show me the difference between the current state of my repository and the changes that I've made. So plus signs mean I've added lines, minus sign means I've removed lines. So for instance, if I edit my README again to delete this line and run git diff, it'll show me all the lines I've deleted and all the lines I've added in all of the files that I've made changes in. In order to commit, I recommend, for now, trying git commit -p. This will walk you through each change. Yeah?
How do you revert to the last
There's several ways. So the sort of best practices way to do it is a command called git revert, which will make a new commit that undoes the old commit. So you see in your log that there's been a revert. You can also do some wonky things like rolling back the history and then, making that you can roll back history as if the commits never happened. But that's kind of unsafe when you're sharing repositories. Yeah?
So let's say that your version is out of date and on your end it says I, and then someone recently pushed something that says I below. On your end, does it have minus signs in front of the O? Like, does it show that you've deleted the O?
That's a good question. Let's replicate that. So let me get through the basic commands, and then I'll show what you're talking about when you're out of date. So here's my current modifications, and if I want to commit it, the kind of safe way to do this is say -p. It'll walk you through each change that you've made. You say yes, you want to commit it, or no, you don't want to commit it. it'll open an editor to ask you to type in what change you made. I've edited the README. And now if you look at my log, I have my first commit and now my new log entry. I've edited the README. And you can see the changes that were committed by running git show. So in practice, I expect a lot of you will just like do this the easy way. So if I make a change to my README, again, the kind of lazy way to do this is to say git commit -m. Here's my new change and the name of the file. So I don't let my students do this, but like my PhD students, because I want a good commit history, but I think you guys can probably get away with this. And so you can see, here's my, this is the new log entry that I made. Okay, so Git is a decentralized repository version control, repository management. So that means that no one copy of this repository is the real copy. There's nothing in the Git system that says this is the real copy. Everyone's copy is the real copy. So if I look at my my copy on GitHub, you can see my README file still says the old stuff before I changed anything. And that's because the log of changes on my machine has gone past the log of changes on GitHub. So in order to synchronize between multiple repositories, push and pull is how you do that. So pull will pull any changes from the remote repository. And so the instructions that GitHub gave you set up the remote repository for you. If you really want to see them, you can type git remote-v, and you can see that there's a remote repository called origin that has the address of GitHub. Pull will take any changes that the GitHub version has and append them to your log so that you can see those changes. And push will take any changes that I have that GitHub doesn't have, my remote repository, and append them to the GitHub repository. So now you can see this is what GitHub thinks my repository looks like now. And you can even explore the log, the set of changes. So this is the commit. This is the last commit that I made. And you can like explore the whole, in a graphical interface. Okay, so that's the basics of Git. I think for practical purposes, what most of you will be doing is you'll be editing in your host machine, and then you'll have some changes to push. So you'll just do what I did here. So I have some changes to my code. You can tell that you have uncommitted changes by running git status. You can commit stuff the lazy way by added compiler phase 1 and the name of the file. You can say git commit -m. I recommend just saying git commit -p, but I understand that that's more time consuming. When you run git status, you'll see that there's no more changes left. And when you run git log, you'll see that it'll give you the confirm that you actually made that commit. And then git push will save it onto GitHub's copy of the repository. That's mostly all you'll need to be doing here. But your colleague asked a really interesting question about what happens when these repositories get out of sync, where two people are making changes to the same repository. So we can actually replicate that by making a new copy of this repository. So I'm going to go back into my Git sandbox. And I'm going to clone it again. So this is how you would, if the repository is already created, like when you make the toy compiler, you'll use git clone to save it. By default, it'll clone it into a folder that has the same name as the Git repository. So on the left here, I've got one copy, one clone of my repository. On the right, I've got another clone of my repository. If I look at their logs, the logs should be identical. So I clone them both from Git. They're the same on Git. So what happens if I make a change here? So what was the scenario you were setting up?
Like if your original file says I
So did it originally say hi?
Yeah.
Okay. So let's get into a state where all the readmes just say hi. Oh. Okay, so I have my log here. I push so that GitHub's copy of README just says hi. And this is my second copy, so it's still the old README because I have not pulled from the other repository. I could pull from either folder, I could pull from any Git repository that I can access with the URL. Okay, so now all of my copies are in the same state. So GitHub, this left copy here and this right copy. So what was the scenario? So on one you add a message, right? So now on one copy it says hi change, and on the other copy what happens?
If you run Git, does it show that like you're missing the change?
Oh, no, it doesn't. So you wouldn't know unless you pulled from that repository.
Okay.
So technically what pull does is it runs this command called fetch and then merges your changes. So if I,
Always when you change something that was previous,
it's not going to show you the difference between the remote repository until you pull those changes. And then it will show you that there are differences between that repository. So yeah, you have your working directory, which is like the edits that you want to commit, and diff shows you the difference between that and your current repository. But the differences between repositories, you use fetch to do that. You have to. They're basically like different. Yeah, they're different branches. You won't have to worry about this since you're not like editing with multiple people. But the real challenge is what happens when people do two different edits and they need to merge those. That's where challenges come in. Sometimes you need to hand resolve the conflicts if they're changing the same lines. Typically, diff and git are good about figuring out which lines have changed independently. So it'll automatically merge them. So if two people have made changes to different parts of the file, it'll add all those changes together. But sometimes it won't work. Sometimes that won't be the safe thing to do. And you still have to kind of manually make sure this is all correct. All right, good questions. Other questions about using Git? So I kind of went on a lot of tangents there, which I probably shouldn't be doing, but the basic thing to remember is these are really the only commands you're going to need for the project. Once you clone your project, and you just follow the directions on Git to do that. Once you set up your key, follow the directions on Git to do that. These are all the commands you'll need in order to submit your projects. So you edit them in your copy of the repository, commit them, and push them. Make sense? All right, other questions about Git? All right, so that brings us to the end of the command line tutorial. I know that was probably a lot of content if you haven't seen this before. I am recording this. Let me make sure it's still recording. I'm recording this, so this will be online. I also have the last offering of this where it's probably very similar, but maybe you can watch that recording too. But there's a really small number of commands you need in order to be successful in this class. You have to have a change directory into the vagrant directory, use Git to push your code, and that's pretty much it. But I just want you to be aware of some of the more advanced stuff you can do on the command line, and hopefully, if you're interested, you can learn more and get some muscle memory so that you can be really fast on the command line. All right, other questions before I move on? Yeah. The labs will be review, so it'll be pretty open-ended, I think. Yeah. If there's anything specific you want for the labs, we'll go over homework, review the class. If there's anything specific you want, let me know. Ask on NetStem, and we can accommodate. this is quite small. All right, so for the last part of this class, I just wanted to go over how your C program, which is just a text file, it's just ASCII code. There's no computational meaning to it, it's just straight text, that no machine that I know of is actually going to execute and run on its own. There's no processor that I know of that takes ASCII C programs and executes it properly. And so there's a whole stack of software that enables you to just write text, which cannot be computed by a machine, to turn it into an actual running program. And the compiler is one integral part of that. You'll be building a compiler today. But in order to build your compiler, you'll actually have to be using a compiler. If you remember the bootstrapping problem from last time, you'll be using a compiler to do that. And so it's good to know about how those system tools work, how the tools work to take your compiler source code and turn it into a running program. And so these are the stages that your source code goes through in order to go from text to be an actual running program on your hardware. So we have your source code. First step is the C preprocessor, which I can show a little bit of. And this just basically takes your header files and copies them in, gives you one giant C file. Then after preprocessing, this C source code goes to the C compiler, which converts it into assembly. And you can actually, see, it's GCC, you can actually have it show you the assembly. Then the assembly code gets taken by the assembler and turned into binary machine code. Even though we have machine code at this point, we're not ready to actually get this thing running. For instance, if you call printf, printf is code that's somewhere else that you need access to be able to run. So the next step that happens is linking. And linking takes multiple compiled object files, multiple compiled binary files, and combines them together. And this is not strictly necessary to run a program on your hardware, but it's really useful if you don't want to have to write printf every time you want to print something. You want to be able to use other people's code. So the linker will take other pieces of code, maybe other pieces of code you've written, other pieces of code that are shipped with your operating system, and combine them together and turn them into an executable format that the operating system understands. And finally, once you have this executable in the right format, the operating system will take this executable, it'll load the machine code into memory, point the program counter or instruction pointer of the machine at the entry point of that program, and just let it run. And now you finally have a running program. Okay, so so I have the diagram. So these are the phases that it goes through: preprocessor, compiler, assembler, linker, for the front end, from source code to an executable. All right, so let me show a little example of each step in this process. So let's take that, I had that print program. Let's go back and use that print program. I don't remember where I put it. Oh, project scratch. Okay, so I had this printer.c file, and these pound statements where they start with pound, these are actually preprocessor instructions. There's nothing in the C language proper that knows what to do with this. And all include does, you may be surprised to learn, is literally just cut and paste the contents of standard.io.h into your C file. That's literally all it does. So let me show you what this looks like. So CPP is how you can run the C preprocessor by itself. So I'm going to run C preprocessor. Its extension is by convention .i. So I'm going to output to printer.i, and I'm going to read in printer.c. Okay, so let's take a look at what printer.i looks like. So it is a very long, cumbersome file. You can see I'm scrolling through this whole giant file here. And all the way at the bottom, here's the text that we actually wrote in our printer.c file. There's our fprintf, there's standard out, and there's all sorts of these other line flags that tell us what line number we were on in the original file, because copying in code blows away your line numbers. But what's all this above here? This is all standardIO.h. StandardIO.h is a massive file that just declares all of the standard IO libraries API, defines its API, defines all the function calls. So if I search for printf, fprintf, you'll see what all that header did for us was it gave us a declaration of the fprintf function. That's it. Nothing else. There's no library code being implemented. It's not really a library. It's just literally another C program that got cut and pasted into your C file. Yeah? Where's the definition? That's a great question. So that header file is not the definition of the function. It's only the declaration. And the reason you need that is because if we just, I mean, GCC is smart enough to do this for us automatically, but if we comment out this standardIO.h, which is kind of hard to read, I probably need a, can anyone not read that? All right, that's, okay. I don't remember what it is on the fly. I will fix this. But if you comment out this standard IO, that's all I'm doing, and try to compile this again. GCC is going to warn us that standard IO is not included. But what's really going on is fprintf is just an undeclared symbol. So if you were to declare some random function in your program, well, your compiler doesn't know what that function is, doesn't know what to do with it. So what these header files do is they just, by convention, they just declare a bunch of functions, your API calls, so that your compiler will be able to type check them. We'll be able to check and say, oh, I know about that symbol. But that's all it does. And the question was, which is a good one, is where's the actual binary code? And it's in this diagram. You'll see that the actual definitions, the binary of your library code, doesn't actually get incorporated with your program until well after compiling and assembling. It's not until linking and loading that the actual code of printf is made accessible to your program. Okay, so let me get through the rest of these phases here. So we've got the preprocessor, and then everyone knows the compiler. If you want to see just the compilation part going to assembly, you can use the -S flag. So if I compile my printer program, and I think I turned off optimizations to make it look more legible. So if I compile my printer program, I've now got this printer.s. I don't have printer.s. Let me put back in. Let me put that header back in. Yeah, there's printer.s. So now you can see what the actual output of the compiler is. It's an assembly program. So I think everyone had to take computer organization, right? So you've done some assembly. This is Intel x86 assembly, so, you know, but don't worry about that. But you can see here that, oh, it's actually calling fwrite in this system. It's not printf. I guess these newer systems, the library changed. So in the older version of this I did a couple years ago, you'd actually see the call to printf. But I suspect that printf is either through a macro or through something in GCC is replacing the call to, oh, because I did fprintf. Let me just do printf. Oh, okay, it's just calling put_s for put string. So under the hood, the compiler is implementing this API call, this printf API call, using other functions to do it. But this is the call. This is the call that's actually asking the operating system to take this string and print it out to standard out for you, which is the console. So you can see that yeah, so this is the output of the compiler. It's just these small set of assembly commands that actually execute, you turn your program into assembly and actually execute what you want to execute, printf. Okay, so this is assembly code. Assembly code is also just an ASCII file. It's not machine code, it's just ASCII. So it's the assembler's job to take this ASCII code and turn it into binary text. Oops, printer.s. So here I'm giving the assembler my assembly code and asking it to give me machine code. So I can't easily look at machine code because it's binary, it's not ASCII. So if I use less, it's going to warn me. But it's ASCII code. If you want to view ASCII, I'm sorry, it's binary code. So if you want to view it, you can use OD to actually view I think this is octal. You can ask it to view the actual binary. But it's not very meaningful. It's just a string of numbers. So here's in hex my assembled assembly file. The file command will tell you the kind of binary file it is if it knows. So this is the format that's used for binary files on Linux. It's called ELF. Okay, so now we've preprocessed, we've incorporated all the header files we need, we've compiled to assembly, we've assembled to machine code. Now here is where other library code that's needed gets incorporated. Now running the linker is a massive pain, but GCC does it for us, and we can see the linker command by using verbose mode. It'll show us the linker command, and I can show you how onerous it is. There's more to just bringing the printf in. There's the C runtime, which I'll explain a little bit. But there's a lot of stuff that happens at the linker level in order to give you all the code that you need in order to execute this program on hardware with the operating system. Okay. So let me increase the size of this. Where's the LD command? Okay, so all of this is all of the flags that are being passed in order to take your compiled binary, link it with all of the other parts of the system, the standard I/O library, C standard library, the C runtime, and to turn it into an executable file that your operating system will take and run. So part of this is following the conventions that the operating system expects in order to run the program. And part of it is providing all that functionality that you just call printf for. You just simply say printf, but there's a whole bunch of functionality that the C library provides you. This is linking with it. You can actually see the C runtime here, and somewhere in here is the standard C standard library. But anyway, that's why I didn't want to write the command myself. GCC calls it for you. It all manages it all for you. But here is where the actual definition of printf gets used, and I think it's I think the actual I can't remember where the actual text of it is. I think it's in libc. So this libc.so, I think this is where the standard libraries live. So this binary, I believe, has the actual definition of your printf function, pre-compiled into a binary. So does that answer your question? That's where the code actually lives. Okay, so that's the linker. I've linked to some other text here on how linking actually happens in modern systems. Instead of just copying the code in, There's this relocatable code so that the position of printf may appear in different spots, in different memory locations in the binary or in the runtime executable or the runtime process. And that's partly for security reasons. There's address space layout randomization, so it'll put the libraries in different locations in memory. And this is for security purposes. So if you want to read more about this, there's some links here for you. Okay, so in summary, we pre-process, we compile the C code into assembly, assemble the assembly code into binary, and the linker is what brings together all of the library code or your code into an executable binary. And then finally, the operating system takes that executable binary, loads it into memory, and turns it into a running process. And so when you type PS, that's managing the running programs of your system. So you have programs, which are machine code, and you have processes. Processes is just a running program. All right, let me go through this a little bit quickly. So this is more for an OS class. The reason that this is so complicated is that you have an operating system that is managing all of the hardware for you. So if you like, actually, it's a fun exercise you can do with a virtual machine, is you can just basically write your own program that runs on the bare metal without any of the operating system. It's pretty painful because you have to do printf yourself, you have to do all of the process management yourself. And you can think of the kernel as just basically a library that gives you functionality that is common to all the hardware that it's supported. So it abstracts away storage, it abstracts away running processes. And if you take it as just an OS course, you'll see more about this. But and then it protects you from being able to touch the hardware directly. So yeah, basically said this is just a library of system calls, like for creating processes, for managing memory. Okay, so I would say take an OS course if you're interested in how the actual operating system works and provides this functionality to your programs. But basically, when you write that simple printf program, there's an enormous amount of code and a whole stack of code and hardware that makes it possible just to do hello world. It may seem really simple, but there's an enormous amount of machinery that's in place that actually lets hello world work. The part of the operating system, at least for Unix-based systems, there's a system called exec, which actually takes that binary, loads it into memory and everything, sets up I/O. If you were to actually, so we all think that main is where our program starts. At the operating system level, actually, there's an entry point called start that you tell the operating system in your binary code, you give it that start location, and that start location sets up the standard I/O, it sets up the arguments, and then it eventually calls main. So in fact, main is not the actual entry point to your program. The operating system is calling the start entry point, and it's the C runtime that sets up main so that you have all those arguments and all that nice functionality in C. All right, so I won't go over this too much. This is more for an OS course. But this is how you go from just a printf program into something that actually runs and actually does something on your machine. And if you want more info about how running programs actually work in Linux, these are very detailed technical guides on running Linux, on how these actual binaries get run. Okay, so the last thing I want to go over is how separate compilation works in C. So when you run any of the projects, you'll be using multiple C files, and you'll compile them separately and link them at the end in order to make your program. So let me show a quick example of what separate compilation looks like. Let me get to my Scratch folder here. All right, so I have one program called caller. So it defines a function G, which calls f, prints it out, and returns the return value. That's my program caller. and I have another program, call E, this is the definition of F. Okay, so let me compile both of these programs, or both of these C files. So caller.c, caller.o, oops, caller.c and callee.c. Okay, so now I've got two object files, callee.o and callee.o. I just compiled those with the programs that I just showed you. If we look at these binary files, the way the linker knows how to combine these two files, the way to provide the definition of the program, for instance, printf, is the compiler and the assembler export a symbol table that tells you the address of every function that's defined in this program. So recall that caller.c defines a function called g and calls a function called f, which is not defined in this file. It's defined in another file, just like when you call printf. If you look at the symbol table that the compiler and the assembler produce, you'll see that g has this address, this offset of 49. So here's the definition. This is the location of g in the binary file. And it has an entry for f because it's being called, but the symbol table doesn't know where that's located. It just says it's undefined. And similarly, the callee has an address for f inside of the binary for callee. And so this is the information that the linker uses in order to line up the two files. So it looks at the two symbol tables and says, okay, I've got functions that need to be called here. I have this undefined function f, and I have this defined function f in another object file. And the linker says, okay, well, I see they're the same name, so they must be the same function. And it combines them so that both files have both functions, and all the addresses are updated so that they're at the right offsets in the binary file. So that's kind of the main job of what the linker does. And so if I then, I do the same thing for main. So main is in the same situation where it's calling f and g, but it doesn't have them defined. So if I compile main.c, you can see that the symbol table for main.o defines the main function, but f and printf and g are all undefined. Once I link them into an executable, also, for instance, if I just tried to compile and link main.o, you've probably seen this message before where it says undefined reference to f. That's because the symbol table has f and no other binary files you've given have a definition of f. But if I provide all of the binary files that contain all of the functions that need to be called, no error. And the symbol table for main now has definitions for all of the functions that need to be defined. So there's g, there's f, main is probably in here somewhere, the main is in here. So that's what the linker does. It takes these separate compilation units, these separate .o files, which may not have all of the code for the function definitions, and it combines them. Okay, so I talked about header files already. And then just very quickly, so makefiles help organize this process for you. So you can see I have an example makefile here that has a list of all the source files, callee, caller, and main. It has a little clever code to convert that to a list of files that have the .o extension instead of the .c extension. This command, or this rule, will tells you how to make all the .c files. Make all the .o files depending on the .c file name. It's a wildcard. So it says run GCC on all the C files in order to give you the .o file. Main says take all of the object files, the .o files, and compile them together into a program named main. Clean removes everything. So I'm going to give you makefiles. We don't have to learn too much about makefiles. They're kind of fun, but they also do dependency checking. So if you've updated one of the source files, it'll check which things need to be updated and only build that part instead of having to recompile your whole program. But I'm going to give you the make files for this class. But that's just a quick overview. Yeah.
Is the object file linking them manually like that's normal, or
Yeah. This is how you have to do it. You know.
you can't just put all the files into GCC?
You could put all the GCF files there, but if you do that, then you have to recompile everything every time you recompile your program. So the benefit of having separate files is that you only have to compile part of your program in order to recompile the whole thing. Modern languages will do this as well. It'll be more automated. But yeah, this is incremental compilation. And make files are the classic way of setting that up. Yeah?
So because standard.io.h is just a header file, does that mean that if you have the contents of it, you could just copy paste the print
Yeah.
part of it?
100%. You could just copy paste that, that definition. In fact, that's what I did here for the caller. If you see here in the caller file, I don't have a header file. I just put extern int f. So you could literally just copy extern print f, and then you want to have the right function signature for it. And then it'll work the same way because the compiler is not actually doing that linking. It's not actually linking the two. As long as the type signature, the function signature is the same, it's not going to care. And in fact, you could replace printf with something else if you wanted by linking with a different program that also defines printf. It's really all up to the linker that actually does the actual combining of the compiled C programs. Yeah, so that's making this is the classic make file. You compile each C file to an O file and then link those, compile those instead of just saying GCC and then a million C files. For small projects, it really doesn't matter. For like the Linux kernel, which has like 20 million lines of code, 20,000 C files, yeah, you don't want to have to recompile your whole kernel if you're doing like development or like a web browser or something. Yeah, incremental compilation is like standard. I mean, this is why the linker exists. It exists for this purpose. You don't have to have a linker to write a program, but if you want to do incremental compilation, you do. All right, so we saw lots of shell commands. Go through the video if you want to review them more. We saw Git usage. We saw how GC and make work together to do incremental compilation. And that's it. So I put some additional resources here. You can look on the notes. Have a good weekend, everyone.
So, I noticed you